Welcome, Professor Sen. Unmute karo. Unmute karo.
Unmuted. Yeah, thank you. Thank you, Professor Brahmachari.
Thank you. So we rejoined once again for the next session, and it's my actually pleasure to welcome Professor Pratik Sen from IIT Kanpur, who is very much well-known to us. As you all know, I'm not citing. So welcome, Pratik, who will act today as the external expert for the open PhD Bhabavosi examinations of Tamanna, our student Tamanna Malik, who did his PhD under the direct supervision of Dr. Najrin Ara Begum. So welcome you once again. And Tamanna, are you ready with your highlighted PPT?
Yes, sir.
Najrin, have you joined? Najrin?
Yes, Gautam.
Okay. Then নাজরিন তুমি মিট করো হ্যাঁ ঠিক আছে ওকে so Tamanna actually as you already presented your research in the pre-PhD examinations in detail, so I request you to present your research in a very highlighted form so as to complete it within 30 minutes or so. Okay. So with these few words, I invite Tamanna to present your research in a highlighted manner. Tamanna, please.
Thank you, sir. Good morning, everyone. Today I am presenting my thesis work entitled Naturally Occurring Bioactive Compounds and Their Synthetic Analogues, a detailed study on their spectroscopic behavior and application in the synthesis of process nanomaterials. Before going through the detail of my work, I would like to give a brief introduction about some terms associated with my thesis title. Now let's break the thesis title into pieces. First, we focus on my first topic, naturally occurring bioactive compounds, and these are the 6 major classes of naturally occurring bioactive compounds, and among them I am focused on the alkaloid naturally occurring, and there are vast range of alkaloids, but we mainly focus on the carbazole alkaloids. This is the basic structure of carbazole alkaloids. Some special characteristics properties of carbazole made us interested to work on this type of compounds. In this slide, this is the spectral behavior of the simple carbazole type of compounds, and as you see that we change of the spectral pattern and the structure, we change the structural pattern, the spectral behavior also changes. Here the carbazole analogues immense popularity in the two stream pharmaceutical and materials. Now my next topic is nanomaterials, but my only interest towards the process nanomaterials. Here, I am interested towards the fluorescence gold nanoparticle, fluorescence silicon nanoparticle, and cadmium sulfide quantum turn by non-covalently and covalently linked carbazole analogues. After a brief introduction, now focus on my thesis. It is divided into 4 chapters. Chapter 1, exploring the propensities of fluorescence carbazole analogues towards the inhibition of amyloid aggregation in type 2 diabetes, an experimental and theoretical endeavor. More than 30 incurable fatal diseases like Alzheimer, Parkinson, and type 2 diabetes caused due to the amyloid aggregation. Hence, it is urgent need to search a therapeutic agent. Natural product and carbazole analogues have the potential towards A-beta amyloid aggregation and neuroprotection. But inhibitory activity of carbazole towards islet amyloid aggregation is still in infancy. islet amyloid polypeptide and insulin co-secreted from the pancreatic beta cell, and the spontaneous misfolding of IPP cause abnormal aggregation that deposit on the pancreatic beta cell and sometimes cause cell death. That is one of the key factor of type 2 diabetes. Indian curry leaf have the potential of anti-diabetic activity and the rich source of carbazole alkaloid. Hence, we selected the 5 structurally different synthetic and naturally occurring carbazole derivative for the inhibition of the amyloid aggregation. This is the synthetic route of the carbazole derivative and the isolation procedure of the mohanimbin that is naturally occurring and their characterization data. Here the UV visible and the process spectral pattern of the carbazole all 1 to 5. This distinct chlorophoric and fluorophoric characters was potential used further to detect the change of the spectral pattern in presence of biomacromolecule. Here we have used the human insulin as a model amyloidogenic protein and the inhibitory activity of the 5 structurally different carbazole analogs towards the inhibition of the insulin amyloid aggregation. At a regular interval of incubation time period, insulin amyloid aggregation formation kinetics in presence of the carbazole was monitored by using THT fluorescence assay. And now, it is the formation of the amyloid in absence of the any inhibitor at regular interval of time by using the fluorescence THT assay. And from the plot 1 to 5 indicate the same in presence of the inhibitor. These carbazole analogs were found to inhibit amyloid growth as denoted by the diminished fluorescence intensity of the THT compared to the control system. However, CZ3 and CZ5 were found to be most efficient in controlling the misfolding of insulin. The structural pattern of carbazole analog may play a key role regarding their inhibitory activity towards amyloid aggregation. Hence, by using the THT fluorescence assay, we can calculate the percentage of insulin amyloid aggregation inhibitory activity by using this equation. And we can found that the inhibitory activity of CZ3 and CZ5 55.4% and 53.5%. And also the insulin amyloid growth kinetics in absence of and presence of the carbazole analogs shown here and the extended lag phase of the CZ3 and CZ5 indicate the slow nucleation process of the formation of amyloid. Then, how to understand the inhibitory mechanism? First, characterize the amyloid by CT and the TAME experiment, and the interaction between the insulin and IPP was done with the help of steady-state fluorescence spectroscopy, molecular docking, and DFT-based quantum mechanical calculation. And from the interesting result obtained from this experiment, we can use it in the biological system, that is mice model. And these are some biological assays. Here, the CG spectra in the absence of CZ3 and the presence of CZ3. In absence of CZ3, with increase of incubation time, a gradual decrease of the peak minima at 208 nanometer and 220 nanometer were observed, indicating the decrease in the content of alpha helix. But in presence of CZ3, the formation of the beta-rich insulin aggregation is slower in comparison to the absence of CZ3. These are the summarized result of the CD analysis of conformational change of human insulin in the absence and presence of CZ3 during different incubation time period. Hence, the CD spectral data clearly indicate that CZ3 is able to prevent some extent the transformation of alpha helix to beta-sheet structure. Now, to understand the morphological change of the insulin amyloid aggregation in the absence and the presence of carbazole analog CZ3. Here, in presence of CZ3, there are few aggregated part was observed, but and the morphology is closely resembled to the human insulin. But in absence of CZ3, there are very densely packed fibrillary structure was observed. This is probable because the CZ3 undergo a favorable binding interaction with insulin monomeric unit. Hence, we are very much interested towards the interaction of carbazole analog with insulin by fluorescence spectral check. This is the fluorescence emission of human insulin in the absence and presence of different concentration of CZ3. Here, with progression of the addition of CZ3, if peak 1 gradually diminished and the peak 2 gradually enhanced, and a new peak arises at 504 nanometer. Similar experiment was done in case of CZ5, and the fluorescence emission spectra of CZ3 and CZ5 in the absence and presence of insulin was observed here, but there is no special change was observed. Now, to understand the binding interaction and their mechanism, we can calculate the binding constant, that is Stern-Hallmark constant, by using the Stern-Hallmark equation. These are the binding constant of the CZ3 and CZ5 respectively. And to further understand the binding interaction of the carbazole analog with insulin, we can perform the molecular docking study, and the resulted binding free energy in case of CZ3 and CZ5 is higher compared to the other carbazole analog. And here the selected bond length of insulin CZ3 and insulin CZ5 dot structure shown here. Similarly, the selected bond length of IBP CZ3 and IBP CZ5 dot structure shown here. And the CZ3 is able particularly to the segment of 20 to 29 of IBP and prevent the change of IBP from the helical peptide to the beta C5 structure. Now, the DFT-based quantum mechanical calculation and involving the two representative carbazoles CJ2 and CJ3 was used for the better understanding of the binding interaction. And here, CJ3 and CJ2 both have the N-methyl group, but unlike CJ3, CJ2 have lack of the formal group at the 3 position. Hence, and from the binding energy value of CJ3 indicate that the formal group have play a key role in this purpose. Now, from this we can check the toxicity of the CZ3 and CZ5. There is no cell death was observed here, and the CZ3 and CZ5 retain their intrinsic fluorescence activity towards the cellular media. Now, for the experiment in the mice model, we can adapt 4 type of mice model, and a different concentration of CJ3 was used here. But there is no significant behavioral or body weight toxic alteration change were observed for the CJ3 treatment mice in comparison to the control. Hence, after that, the THT staining histological section of the pancreatic tissue isolated from the high fat and high carbohydrate diet fed mice with different concentration of CJ3 shown here. But here, the 100 microliter per kg body weight is the optimum dose. Now, the staining of the histological section of the pancreatic tissue isolated from the 4 different mice group with an amyloid staining agent, THT. In control system, the extent of islet amyloid deposition was negligible in the standard diet-fed mice. Negligible deposition was also observed when injected CJ3 in the standard diet-fed. And the amyloid deposition was quite high in the high-fat and high-carbohydrate diet-fed mice group. Significantly less amyloid deposition was noticed in the high-fat and high-carbohydrate diet-fed mice treated with the CJ3. Hence, we conclude that CJ3 was comparatively more potent than the CJ5, and CJ3 was effectively controlled the islet amyloid deposition on the pancreatic islet cell of the diabetic mice model. In future, structure of CJ3 and CJ5 can be tailored more accurately so that these compounds can be used as a therapeutic agent to eliminate the future risks of Alzheimer's disease in patients suffering from type 2 diabetes. Hence, as CJ3 is a therapeutic agent, but carbazole have the poor water solubility that limits their bioavailability in aqueous medium. To solve this problem, hence, first of all, we incorporate some hydrophilic group in the carbazole skeleton or tagging them with the nanoparticle surface. Tagging them on appropriately modified surface on the hydrophilic nanoparticle is much easier. It will serve 2 purposes. The hydrophilic nanoparticles will carry it in the interior of cell, and the fluorescence nanoparticles will keep fluorescence due to the presence of fluorescence carbazole moiety. This motivated us to our next chapter, chapter 2, the carbazole-based small molecule, functionalist fluorescence silica nanoparticle synthesis application as fluorophore for biomacromolecule and evaluation of the biocompatibility using Drosophila. Due to the hydrophobicity, organic molecule, the lack of the bioavailability, and some fluorescence organic dyes sometimes cause cell toxicity. Hence, it is essential to design a synthesis of the biocompatible fluorescence nanoparticle. And the functionalization of silica nanoparticle with fluorescence molecules is a promising method. Here, the carbazole modified fluorescent silica nanoparticle at first synthesized, and their bioavailability was checked by using the Drosophila melanogaster as a model system, and their intrinsic fluorescence activity was further used for the selective sensing ability towards ctDNA and the enzyme horseradish peroxidase. This is the synthetic route of the carbazole modified fluorescent silica nanoparticle, and the morphology of the carbazole modified fluorescent silica nanoparticle was checked by using the DNS and the FSM image. Here, The mean particle size of the APTS-MS is nanoparticle, and the mean particle size of CMFS are 267.1 and 288.4 nanometer. Here, the efficient image indicate in both the cases there are spherical nanoparticle was observed, and in both the cases a minor aggregated microstructure was observed, but after functionalization of the carbazole, there is no morphological change was observed in case of CMFS and PS. After that, the surface chemistry of CMFS and PS was studied with the help of TGA and weight analysis. From the TGA analysis, means from temperature 100 to 850 degrees centigrade in the temperature range, weight loss for the bare silica is very minimum. For APTS-MS, it is 31.38%, and CMFS and PS is 43.08%. Then the specific surface area was measured by N2 absorption and disruption isotherm of the CMFS and PS is at 77 N Kelvin. And it follows the type for isotherm curve, and the specific surface area are shown here. Now, the UV visible and the fluorescent spectral behavior of the CMFS and PS and the precursor and CZ1 was shown here, and the spectral characteristics of CMFS and PS were closely resembled to CZ1. This is because after the functionalization process, CZ2 converted to another fluorophoric moiety, and which is closely resembled to CZ1. Hence, the strong emission intensity was observed in case of CMFS and PS is mainly due to the surface attached carbazole moieties. After that, we are also interested towards the bioavailability of CMFS and PS in the Drosophila melanogaster model system, and for this experiment, we performed the biological assay. And these are the characteristics biological assay. The effect of CMFS and PS was checked on the development and behavioral change of Drosophila melanogaster, and the phenotypic behavior and thermal sensitivity also checked. But the carbazole are, it is concluded that the carbazole are safe for Drosophila, and the attachment of the such biocompatible carbazole moiety on the silica nanoparticle surface reduce their toxicity, and in the case of CMFS and PS also triggered on their fluorescence activity. Hence, by using the fluorescence activity of the CMFS and PS, we selectively sense the biomacromolecule. Here, the fluorescence emission spectra of CMFS and PS in the absence and presence of ctDNA. After addition of the ctDNA, a gradual quenching of the peak 360 nanometer observed. This is because the non-covalent interaction between the ctDNA base pair and the nanoparticle surface sample carbazole moiety responsible for this sensing. Here also, fluorescence emission spectra of CMFS and PS in the absence and presence of the various biomacromolecule like HRP and SHG. No effective interaction among CMFS and PS and SHG was observed, but in case of HRP, there is a progressive decrease of the 360 nanometer peak was observed, and also the 324 nanometer peak gradually increases. This is due to the increase of the hydrophobicity in the microenvironment of the fluorophore, that is CMFS and PS, in presence of HRP. Now, to conclude that, and the surface attached carbazole moiety impart their characteristics fluorescence activity on the CMFS and PS. This biocompatible and fluorescence nanoparticle may have the potential to be used for the development of biomedical diagnostic and therapeutic tools in future. After the successful completion of the surface attached carbazole modified silica nanoparticle fluorescence, we are very much interested towards the synthesis the fluorescence gold nanoparticle by using the carbazole analogs. This motivated us towards our next chapter, chapter 4, the harnessing carbazole-based small molecules for the synthesis of the fluorescence gold nanoparticle, a unified experimental and theoretical approach to understand the mechanism of synthesis. Here, the gold nanoparticle, the small molecule medicated fluorescence and biocompatible gold nanoparticle have become an ideal candidate for living cell imaging. Recently, a new direction has been opened up towards the synthesis of biocompatible metal nanoparticle coated with biofriendly fluorescence molecule. Carbazole have characteristic fluorophoric behavior as well as non-toxic. These distinct features of carbazole prompted us to explore this compound for the synthesis of fluorescence biocompatible metal nanoparticle. Here is selected 6 structurally different carbazole analog as a reducing agent for the synthesis of gold nanoparticle in different micellar medium, and the red color indicates the reducing side of the carbazole analog, the in situ generated gold nanoparticle catalyze the CC and the NN coupling reaction of carbazole. The experimental and theoretical results indicate the origin of the process of gold nanoparticle. And this is the synthetic route of the carbazole 6, and these are the characterization data. Now the schematic representation of the gold nanoparticle synthesis by using the ethanol stock solution of carbazole in SDS medium. After the synthesis of the gold nanoparticle, then we can to check the UV visible spectra of the gold nanoparticle so for to assure that the formation of the nanoparticle, and these are the different color of the nanoparticle, and the AU nanoparticle synthesized in SDS medium give mostly the broad SPR band except the CJ3 due to the formation of anisotropic nanoparticle. Now, to check the size and the shape of the nanoparticle, we have performed the 10 experiment of the gold nanoparticle, and with variation of the reducing agent and micellar medium, the size and the shape of the particle also changes. And in case of carbazole 6, so various regular geometrical shapes such as triangular, hexagonal in all the three media. Now, we select the three model systems, that is to understand the fate of the oxidized product. And in carbazole 1, 2 probable reduction site in NH bond and the 3 CH bond. And in carbazole 3, the N position is blocked or reduced reduction site is here, the CH bond. A new reduction site is appeared in the carbazole 6, that is the NH2 bond. Oxidized carbazole were from either CC or NN coupled oxidized product. This is the schematic representation of the synthesis of the gold nanoparticle, and the in situ generated gold nanoparticle catalyze the intramolecular CC and NN coupler. We isolate this type of the oxidized product of the carbazole 1 and their characterization data, carbazole 3 and carbazole C and their characterization data. These are the NMR spectra of the key oxidized product. After that, the both kinetics of the gold nanoparticle synthesized by carbazole 1, 3 and 6 in SDS medium shown here, and in all the cases it followed the first order exponential growth function. The rate constant of the growth kinetics of gold nanoparticle in SDS carbazole in SDS medium, carbazole 6 is more higher than carbazole 1 and than carbazole 3. The NH2 group at the 3 position of carbazole 6 took part in the reduction of gold 3 ions to gold 0. And the growth, similarly, the growth curve of the gold nanoparticle synthesized by the ethanol solution of carbazole in the 3 different micellar medium, and the order of the growth kinetics SDS, PPP, and CTAL. After that, we are very much interested towards the fluorescence activity of the synthesized gold nanoparticle, and here we saw that the characteristics emission of the gold nanoparticle may be due to the attachment of the unoxidized and oxidized form of the carbazole in the surface of the synthesized gold nanoparticle. And after that, we are interested to understand the origin of the fluorescence and perform the fluorescence and spectra of the ethanol solution of carbazole in the absence and the presence of the AU3 ion in SDS medium at regular interval time, and it is concluded that it clear evidence that a new fluorescence pattern of the synthesized gold nanoparticle which is closely resembled to the fluorescence pattern of the carbazole and their oxidized form. This is the spectral pattern of the carbazole and their oxidized form, and after that to further understand the if in situ generated gold effect of the in situ generated gold nanoparticle on the fluorescence pattern of the carbazole, we can perform the fluorescence spectra of this carbazole in SDS medium in the presence of the chemically synthesized gold nanoparticle. There is no sign of the change were observed. In situ generated gold nanoparticle was responsible for such fluorescence quenching of the carbazole derivative. And this was further supported the phenomenon by using the computational studies. Here, the intermediate charge transfer state involves an electronic excitation from the donor carbazole HOMO of the donor carbazole moiety and the LUMO of the AU nanoparticle acceptor. And the density of state and the isosurface of the molecular orbital indicate the electronic transition from HOMO carbazole to the LUMO carbazole cluster. Now, this is the possible mechanistic pathway. It follows the radical pathway. First of all, the carbazole AU3 complex form, and after that, the nanoparticle formation, and a radical was generated in the carbazole moiety. After that, the intramolecular or the CC and NN coupled product was formed. This clearly indicates that in situ generated gold nanoparticle acted as a catalyst for such CC and NN coupling of the reaction, and this reducing agent were oxidized to CC and NN couple. Hence, such easily synthesized bis carbazole derivatives are well known for their use as OLED and hole transporting material. which are relevant to organic semiconductor device such as electroluminescence device and solar cell. Now, in carbazole, we explore the carbazole moieties for the synthesis of the fluorescent silicon nanoparticles and fluorescent metal nanoparticles, and both are used in the biomedical diagnostic field. But carbazole itself have some property like OLED, solar cell, and electroluminescence device. Hence, what will happen if we tag the carbazole on quantum dot, and can such carbazole quantum dot system act as a light harvesting material? This motivated us in our next chapter, chapter 4, carbazole decorated fluorescent cadmium sulfide quantum dot, a unified experimental theoretical endeavor to understand their potential as light harvesting material. Here, among the inorganic semiconductor, cadmium sulfide is very much important due to their size-dependent emission in the visible range, photostability, and size-dependent narrow and tunable band gap. And also, carbazole moiety itself may instinct poor device performance due to its planar structure, which is formed to form the aggregation. Hence, the inorganic organic hybrid nanomaterials are just suitable for the designing of the solar cell. And the optoelectronically active carbazole and CDS quantum dot systems can be explored as light harvesting material in the solar cell. And first of all, we just synthesize the organic inorganic nanohybrid system by using the carbazole and CDS quantum dot, and the detailed photophysical study indicate that here a energy transfer, that is posterior resonance energy transfer, occur from carbazole moiety to the MPA cap CDS quantum dot, and the ANC CDS quantum dot signify their potential as light harvesting material in the present world. This is the synthesis procedure of the AMC CDS quantum dot. And the FTIR and orange NMR spectra was used for the successful grafting of the carbazole on the nanoparticle on the quantum dot surface, and comparative orange NMR spectra ensured that successful grafting of the carbazole moiety on the MPA cap surface of quantum dot. Now, the formation and the structure of MPA CDS quantum dots shown here by using the absorption spectroscopy. A broad hum of 386 nanometer observed in case of MPA CDS quantum dot, and from the powder XRD data, it is clear indicate that the three prominent peak was observed, and it's closely resembled to the zinc blend-like structure. And the three prominent peak indicate the 111, 220, and 311 plane. And the size was found in case of CDS quantum dot and AMC CDS quantum dot, or by using the this equation from the UV visible absorption spectroscopy. Now the shape, size, and morphology were checked by using the TEM experiment, and the average diameter in both the cases well agreed with the diameter coming from the absorption spectra. And here the bright spot in the ACD pattern indicate the crystal structure of the quantum dot. Next, the optical property of the MPA CDS quantum dot and ANC CDS quantum dot are compared here. And in the UV visible absorption spectra, a slight redshift in case of ANC CDS quantum dot was observed in comparison to the MPA CDS quantum dot. And we can calculate the optical band gap plot by using the top relationship, and these are the corresponding value of the optical band gap. Now, we are very much interested toward the spectral pattern of the AMC MPA CDS quantum dot and AMC CDS quantum dot. In case of AMC, here at photo excitation 290 nanometer, a prominent fluorescence emission was observed, and MPA CDS quantum dot at photo excitation 400 nanometer, a prominent fluorescence peak was observed. But along with 400 and 290 nanometer, AMC CDS quantum dot responds to a broad range of the photo excitation and keeps the emission spectra throughout a broad range of beats. Its potential to be used further as a white lighting emitting diode in future. And we also compare the excitation spectra of the MPA CDS quantum dot and AMC CDS quantum dot, and a 25 nanometer redshifted in case of AMC CDS quantum dot in comparison to the MPA CDS quantum dot was observed. This result confirms the covalent linking of the AMC on the MPA CDS quantum dot. Further to understand the energy transfer between the AMC and MPA cap CDS quantum dot, that is phase energy transfer, we study here the spectral overlap of the excitation spectra of the MPA CDS quantum dot and the emission spectra of the AMC. and a vast spectral overlap indicate that energy transfer occur from AMC donor to the MPS quantum dot acceptor. That is, there is a freight occur, and from this we can calculate it, some terms like freight efficiency, rate of energy transfer, and distance between the donor and the acceptor. To further elucidate the freight mechanism using the fluorescence lifetime measurement data, we can perform the lifetime measurement by TCS-PC lifetime measurement. And here the AMC and AMC CDS quantum dot and the MPA and AMC CDS quantum dots compare here. And the summarized result of the lifetime profile are shown in the table. A drop of the lifetime of AMC confirmed that an energy transfer from the donor system to the acceptor moiety probable by the freight mechanism. And here some freight parameter for AMC CDS quantum dot conjugated system, and from this, here we summarize the freight parameter for AMC CDS quantum dot conjugated system, and all the freight parameters in favor of the freight mechanism in case of AMC CDS quantum dot, and the donor and the acceptor are situated within the range of the Foster radius. Hence, the occurrence of the efficient freight between the acceptor or and the surface anchored carbazole molecule was observed. Now, here the extended lifetime was observed in case of the hybrid system, and to further understand this, the potential of the AMC CDS quantum dot as a light harvesting material, we can perform the computational studies. And these computational studies, it is clear that the HOMO is situated on the carbazole moiety and the LUMO is situated on the CDS quantum dot, that is acceptor, and it follows the type 2 band alignment of the AMC CDS quantum dot. This type of band alignment also reflects from the projected density of state. These nanohydrates show a clear special charge separation after the photo excitation, and the electron hole recombination is therefore hindered. Such phenomena prolong carrier lifetime and makes the AMC CDS quantum dot worthy for application as light harvesting material. Now we conclude that a detailed photophysical characterization of this nanohybrid system confirms the occurrence of the freight from the carbazole moiety to the CDS quantum dot, and in future the energy transfer efficiency of such carbazole decorated CDS quantum dot can be explored to develop the freight-based optoelectronic sensor and the biomedical diagnostic tool and light harvesting material as well. Now we summarize my thesis here. In chapter 1, naturally occurring carbazole monoamine and the synthetic carbazole analogs 3-formyl 9-methyl carbazole were found to be efficient in the inhibition of islet amyloid aggregation, one of the major factor of type 2 diabetes. Moreover, they can also be used as foolproof for insulin. In future, such compound can be studied for the development of anti-diabetic drug. In my next chapter, the carbazole modified fluorescence silicon nanoparticle inorganic organic nanohybrid system with tailored structure and hydrophobicity, and showed characteristics fluorescence activity and bioavailability with the Drosophila model system. In future, this biocompatible and fluorescence MPS may have the potential to be used for the development of biomedical diagnostic and therapeutic tools. In chapter 3, we have able to shed light on the mechanistic pathway of the carbazole mediated synthesis and origin of fluorescence of AU nanoparticle. Hence, the in situ generated gold nanoparticle acted as a catalyst for such CC and NN coupling of carbazole. In future, such easily synthesized bis carbazole derivative are well known for their use as OLED and whole transporting material. In my last chapter, carbazole analogs were explored further to synthesize the inorganic organic nanohybrid CDS quantum dot system showing potential as energy material. In future, the energy transfer efficiency of such carbazole decorated quantum dots can be explored to develop the freight-based optoelectronic sensor and light harvesting material. The list of the member, I would want to acknowledge them, and these are my publication list, and thank you.
Thank you,
Thank you,
Tamanna, for maintaining the time, actually. Okay.
Thank you, sir.
and very lucid presentations. Um, Now the session is open, and I first invite our external expert, Professor Pratik Sen, to interact with the candidate with his queries and suggestions. Very particularly, I have noted that Professor Sen has little bit very queries, and you can ask the candidate your queries, and also give your suggestions that will help the candidate in her future research. Professor Sen,
Yeah,
please.
yeah. Thank you, Professor Brahmachari, for allowing me to ask or interact with the candidate. And first of all, I'd like to congratulate Tamanna to generate a lot of data during her PhD tenure and publishing so many papers in good referred journals.
Thank you, sir.
And obviously, I also would like to congratulate you for presenting more than 90 slides in like a Shinkansen manner in 30 minutes time. So anyway, so I have few queries and also some questions as this is a viva voce examination. So I'll go one by one, maybe for 5 minutes or so. So can you can you tell me? I mean, why you have incubated insulin at 72 degrees centigrade? Why this particular temperature?
Yes, sir. At that particular temperature, first of all, the insulin monomeric unit converted to the misfolded was occurred, and after that, a oligomer was obtained at that particular temperature, because insulin is very much stable at the temperature at 5 degree or 0 degree centigrade temperature. Hence, we perform this experiment at 72 degrees centigrade temperature.
No, I understand that higher temperature insulin will unfold and then you will have. But why such a specific temperature, like a 72 degree?
Sir, from literature survey, we obtain that procedure, and in this and as we follow the 72 degrees centigrade temperature.
Okay. So you have used thiaflavin T emission for monitoring the amyloid formation.
Yes, sir.
So do you know the photophysics of thiaflavin T? Why it shows such kind of can be used as the amyloid marker and fluorescence intensity increases as amyloid is forming?
Yes, sir. And can I show the slide?
Yeah, yeah. You can go to the slide.
Here, the thiaflavin P has a single bond, rotatable single bond, two rotatable single bond, and when the thiaflavin T bind with the aggregated amyloid, its environment was changed, and it is quite viscous, and the thiaflavin T is quite rigid enough. That's why due to their planar structure, it gives the higher fluorescence intensity when it binds towards the THT, towards the aggregated amyloid structure.
Okay. So in your next slide,
Yes, sir. Yes, sir.
you can keep the slide on. In your next
Yes,
slide,
sir.
I mean, you are measuring the fluorescence intensity in presence or absence of your
Inhibitor.
these carbazole derivatives.
Yes, sir.
And you saw a decrease or the intensity increase in the intensity is not as much as without the inhibitors.
Yes,
Right?
sir. Yes.
Okay, so now because of the amyloid formation, right, the system will also become little turbid. Am I
Yes,
correct?
sir. Yes, yes.
So did you take care of this change in the optical density of the solution during this experiment at the excitation wavelength? absorbance of the solution, because you have excited at 400 nanometer. If I
Yes, sir. Yes. I had performed this experiment the absorption spectra, but the carbazole moiety interfere in the region where the insulin amyloid aggregation spectra also observed. That's why we cannot interpret properly from this absorption spectra.
no absorption spectra, I understand. I mean, there is an overlap between the
Yes.
carbazole absorptions and thiaflavin T absorption, but the incoming light which you use to excite either of this thiaflavin T, that incoming light will not be available to thiaflavin T because of the presence of carbazole, as well as because of the formation of the amyloid, which become turbid and induces scattering in the solution. So how did you take care of that? That is my question. So if you have this absorption spectra,
No, sir. The aggregated amyloid with the carbazole, this is a clear solution which I performed the experiment.
now, okay, do you have this some background noise? Do you have this absorption spectrum of carbazole?
Yes, sir.
Can you show?
Yes. Here, the absorption spectra of the carbazole and the only the carbazole, the basic structure of carbazole indicate in the black color, and other is the functionalized carbazole molecules.
So it does not absorb at 400 nanometer. That's the answer to your
No, sir.
Okay, okay, good. Okay, so if you can go to this slide 24.
Yes, sir.
So the fitting equations, right? What you have used,
Yes, sir. Yes.
and that fitting equation you have used to fit your change in the fluorescence intensity as a function of time, and so you can find the lag phase.
Yes.
So did you derive this equation by yourself?
No, sir. By using the origin software.
No. I'm not asking about the fitting. I'm asking about the equation.
No, sir. I didn't derive this equation.
You should have derived.
I only calculate the value from using this equation, and
No. I know these equations is known equations, and it's
Yes.
available in the literature.
Hmm.
But still you should have derived, because there is a assumption behind the derivation of this equation. So
Okay.
are you aware of this assumption?
No, sir.
What is A1, what is A2 in that equation?
A1 and A2 is the initial and the maximum fluorescence intensity respectively. That is the in A1 when the amyloid formation is occurred, and A2 is the after 72 hours of incubation.
Exactly. So
Yes.
as you can see here in that whole equation, right, you have two extreme points, and now
Yes.
you are calculating the intensity of the intermittent points.
Yes.
So it tells you that intermittent points are a linear combination of the two extreme points.
Yes, sir.
You
I can understand.
Yeah. So when you can do so, when you can apply such kind of assumption to your system, because it is a linear combination of the two extreme points. Like any thermodynamic parameter, when people try to measure experimentally, they also take such kind of assumptions.
Okay.
The assumption is that system has to be reversible in nature. If it is not reversible, then you cannot apply such kind of analytical techniques, right? Or you cannot determine the delta G, delta H, all those with temperature dependence like that. So that leads to my question: did you check the reversibility of this process?
No, sir. I didn't check it. In
Okay,
this
so
case.
yeah, I mean, in future when you will do such kind of work, better to check the assumptions taken to derive the equation which you are going to use, and
Okay,
whether
sir.
that equation is applicable to your system or not.
Okay, thank you for your suggestion, sir.
Okay, so can you go to slide 28?
Yes.
So probably I missed your explanation. I mean, what is the origin of that peak at 500 nanometer?
The 504 nanometer is appear due to the carbazole analog of the CJT. This is mostly the formyl group present at the 3 position of the CH3. Sir, can I show the fluorescence spectra of the CJ3?
Yes, yes.
The blue color indicate the fluorescence spectra of the CJ3, and here nearly about to 500 nanometer, there is a peak maxima was observed in case of CJ3. Hence, when after addition of the CJ3 in the insulin in the human insulin medium, a new peak arises at the 504 nanometer. This is mainly due to the carbazole analogs.
Okay, so this is because of the carbazole analog.
Yes,
So
sir.
this carbazole analog is having two emission maxima. One is around 360, 70
Yes,
nanometer.
sir.
Another is at 500 nanometer.
Yes, sir.
So usually, I mean, if it means that I have two different emissive states
Yes, sir.
in that CJ3 molecule, right?
Yes, sir.
Any idea what is the origin of these two different states, and whether there is a change in the structure or something like that, in excited state reactions like that?
In the 386 378 nanometer, the emission spectra is mainly due to the pi transition. No,
Mhm.
it is the n pi transition.
No, I mean, see, usually these molecules are going to have this intersystem crossing
Okay, okay.
and leads to the stable isomer, like it follow the Kasha's rule.
Yes.
But still you are having two different distinct emission. I mean, even you don't want to see see it here in your previous slide where you showed this carbazole emission. So there is also that same thing is visible, right?
Yes.
You have this carbazole CZ3 structure. Can you just
Yes,
quickly?
sir. And this is the structure of the CZ3.
Okay. So now looking at this, I mean, in the excited state, do you feel that there could be a possibility of any reactions, any protonation somewhere, and then
The formyl group is the responsible part here.
yeah, because okay, okay. So think about that. Hmm?
Okay, sir.
Okay, so when you measure this fluorescence spectrum, did you corrected the observed emission spectrum, or do you know the correct how to measure the correct fluorescence spectrum?
Uh, yes, sir. Here I did not corrected the emission or absorption spectra, but I know that the corrected spectra is that where there is mm, there is if there is no error in the there is no error or obtained from the machines with emission and the absorptions when we perform the emission
No,
and
no.
the absorption spectra.
Tamanna, for your information, there is nothing called the corrected absorption spectrum, because absorption spectrum is always corrected in terms of that quote unquote corrected, which is originated from the machine.
Hmm.
Right? Because the
Okay.
sensitivity of the monochromator, I mean the throughput of the monochromator and the sensitivity of the detector depends on the wavelength of light, which actually get cancelled in case of absorption spectrometry, but in case of fluorescence spectroscopy, that is not getting cancelled. So
Okay.
if you are not aware of that, I mean, please check that later on. So
Okay,
that
sir.
in future, whenever you will measure the fluorescence spectrum, you know that what you should do.
Okay, sir.
Okay. So can you go quickly to this slide 44?
Yes, sir.
You have highlighted. You have highlighted. There's some problem in that voice feedback. Anyway, so this zeta potential value,
Yes, sir.
what does it signify?
Zeta potential value means uh, charge density on the surface of the nanoparticle.
Why you want to highlight? What you want to tell from this
After
observation?
here we perform the zeta potential value. This is because the after the functionalization of the carbazole analog, the silica nanoparticle surface, the zeta potential value quite transfer to the positive value, because in case of bare silica literature know that the zeta potential value is positive, but after functionalization and the value is converted to the positive value due to the surface modification of the silicon nanoparticle.
Okay, good. So this experiment was, I mean, this curve, this particular diagram, that size versus intensity.
Yes, sir.
How did you measure this?
By using the DLS experiment,
What is the full form of DLS?
dynamic light scattering.
What is dynamic about it?
When we put a sample in a machine, the light
No, light scattering, that is a different story. And why the dynamic? Where is the dynamics here? Why we called it as a dynamic light scattering? Do you know this machine? What this machine actually acquired during the measurement?
the hydrodynamic diameter.
No, 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 no. Raw data. What is the raw data out of this DLS machine? Hydrodynamic diameter is a calculated one. And what is
Yes.
the assumption to get this hydrodynamic diameter? What is the assumption is made?
The water molecule or the solvent molecule which we used for this experiment also mm,
No, no, no. Which equation is used for the measurement, for the determination of this hydrodynamic diameter?
sir, I don't know.
Stokes-Einstein.
Okay.
And what is the assumption for that? Because the machine collects something and then it convert it, do some mathematics, some analysis, and then it gives you this type of data.
Okay.
So the assumption in this case that it assumes that the particle is spherical in nature,
Yes.
and it follows the Stokes-Einstein behavior. Stokes-Einstein behavior means the diffusion, the diffusion is normal. It is not a hyperdiffusion or hypodiffusion. It's a normal
Okay.
design. and it collects the fluctuation in the scattered light intensity as a function of time, and then it correlate that fluctuation. That is called this as a function of time. That's why it's called the dynamic time.
Okay, sir.
So my suggestion is that whenever you will use any machine, because you have used so many instruments
Yes, sir. Yes.
during your PhD, I mean,
Yes.
it's always better for you to understand the basic principle of those instruments, right?
Okay, sir.
Okay, very good. So now you know the scattering of light,
Y-
right? You know,
Yes.
you studied. Obviously, I know Vishwarati chemistry department. So you must have studied the light scattering. So what type of scattering you know?
Sir, I do not have any idea about this experiment.
No, I'm not asking about this experiment. I am asking about the scattering phenomena. Do you know the scattering phenomena?
Oh,
Like there are basically two different types of scattering broadly divided into one is elastic scattering, another is inelastic scattering.
okay.
So now, if I ask why sky is blue, can you answer that question? You must have figured it out that it is related to scattering
Yes, sir.
because I am asking now. Anyway, no issue. So can you go quickly to slide 77?
Yes, sir.
This is my last question. I'll not ask any more. So
Okay, sir.
you said that there is a Foster resonance energy transfer between the ligand, the carbazole moiety, to the cadmium sulfide nanoparticle.
Yes, sir.
What led you to conclude this statement, or how did you make such kind of a conclusion?
Okay, sir. First of all, we perform the spectral overlap between the excitation spectra of the MPS-CDS contourer, that is acceptor, and the emission spectra of the donor, that is carbazole moiety. And we observe that a vast spectral overlap was obtained here, and hence it is one of the criteria of the third experiment. And after that, there are some fate measurement, that is the distance between the probable distance between the donor and the acceptor is within the range of 1 to 10 nanometer, and in our experiment.
Okay, hold on. So you calculated that R equal to 7.4 nanometer.
Yes, sir.
To calculate that, you have used the fluorescence lifetime data.
Yes, sir.
Okay, so how did you calculate R0?
I calculate the R0 equation by using this equation here. By using this equation, and here the J lambda value, that is the spectral overlap integral, calculated by using this equation, and here the FD value indicate the sum of the fluorescence intensity at the particular wavelength where the spectral overlap was observed, and the epsilon value is the sum of the epsilon value is also the also the sum of the here between the wavelength region where spectral overlap was obtained, and from this equation we can calculate.
Kappa square
Sir?
in R0 equal to something multiplied by kappa p.
Kappa square is the transition dipole or dipole of the donor, that is, and it is here the 2 by 3.
Is it the transition dipole of the donor, and how this value become 2 by 3? That's my question. I wanted to ask you this question only, so other things were the preamble.
In the here we use the 2:1 water ethanol medium, and
No. 2:1 is nothing to do with this 2/3.
No, sir.
So come to the point. Why did you take this kappa square value as 2/3? You only did and published nice papers.
Yes, sir. The transition dipole of the donor here used 2/3.
Again, I'm telling you, this is not the transition dipole moment of the donor. It depends on the orientation of the absorption and emission transition dipole of the acceptor and donor. So that is a function of theta.
Okay, sir.
So there is a main question. What I want to ask is that cadmium sulfide nanoparticle. How did you define the direction of the transition dipole? Because it is a sphere. Is it meaningful to calculate the R0 value for a spherical nanoparticle and with a dye molecule covalently or non-covalently attached to it? So if you have not gone through this kappa squared thing, then it is not good to ask you this question. Okay, so can you go to, okay, I have one more question to ask you. That is my last one. Slide 80.
Yes.
Here you showed the powder XRD pattern.
Yes, sir.
What is the principle of powder XRD pattern? I mean, principle behind getting this pattern.
The crystal, the powder sample.
So I'll give you a hint. Bragg's equations, right?
Yes, sir.
So tell.
When the in light there are three prominent peak in correspond to the one on and the three plane and the three plane.
So it is. If you consider the first order diffraction, then lambda equal to d sine theta.
Yes.
So the value of theta, if the lambda is constant, then depending on the
value of
d,
theta.
value of d at different angle, theta will be different, right? And so you are getting
Yes, sir.
for different planes at different angles.
Yes,
But that
sir.
is not my question. My question starts now. As this is a powder XRD sample, this is like a polycrystalline sample, right?
Yes,
powder, right? It is not a single crystal. So that means in a given sample, you have different small, tiny crystals, and the orientation of those crystals are isotropic in nature. Isotropic in nature.
Okay.
So that means for a crystal which is oriented like this way, another crystal may orient like this way. You see my video, right? Orient like this way. So and there is an angle between these two crystals. Although both are 1-1-1 plane, let's say 1-1-1 plane, but there is a variability in the angle. So that means the theta will change automatically, right? Because the incident radiation is fixed. The theta will change, but still you get the value of theta for 1-1-1 plane at a particular angle. Why it is so? You got my question? That is most important. So the orientation of the planes, 1-1-1 plane, can be anything because it's isotropic. This is a powder sample. But still you get a particular value of theta. This is correct. I'm not telling that this is wrong. I'm just trying to understand, trying to ask you the basic things. So what is the reason for that? Okay, so looks like you have not thought of this. So that's what I'm again telling you that please try to understand the basic uh, like mechanism of getting a data from an instrument, right? right?
Okay,
So
sir.
with this, I think your amount of work is fabulous and nice publications. You also have presented well. So with this, I end my questions. Professor, please. Yeah. Professor Bomachari.
Thank you, Professor Sen, for your suggestions that obviously enlightened Tamanna. Thank you. And if there is one or two more queries or suggestions, please.
One question.
Professor Chandra, please.
Yes, sir.
Tamanna, I enjoyed your talk and also many question answering by you to the external expert.
Thank you, sir.
I'm just concerned. Did, did you crystallize this compound?
Which
By means of crystallization, I am talking about the single crystal because cadmium is a second transition heavy metal.
Yes, sir.
It is easy to crystallize. Is it
Yes, sir.
necessary for your study or not necessary at all?
No, sir. Actually, so here we are trying to so here we are try to synthesis the organic inorganic nanohybrid system, and these materials can be used further as a light harvesting material. So this is our main motto for this work here.
No, that's okay. But because on the single crystal,
Yes,
you know the quantized data and very crucial data
yes, sir.
sometimes. My question was whether it is necessary for your study or not at all.
No, sir.
Not necessary, right?
Yes.
So single crystal is not needed. As external expert indicated to you regarding some of the alpha, beta, gamma, etc., and several angles and molecule structure, along you indicated TEM data, that can be explained in a greater detail, I think. Okay, Professor Brahmachari, please.
Thank you, Professor Chandra, for the suggestion. If we can take only one queries or suggestion. Hopefully, there is no more queries. Thank you.
One suggestion.
Yes,
Yes,
please.
sir.
May I qualify enough to give a suggestion?
Yeah,
Okay.
obviously, you can suggest.
Okay, please, I am suggesting not at this level, but still, if you single crystal gate and structure, sometimes it is difficult. Maybe not as difficult for the other metal, as for example, non-heavy metal. It is easy. Then
Okay, sir.
you may get some crucial as well as the scrutinized data.
Okay,
Okay,
sir.
thank you.
Okay, sir.
This is
Thank you.
suggestion.
Okay, thank you, sir.
Thank you once again, Professor. Actually, Tamanna, you please take note of the suggestion, and
Yes.
you can implement in your further research area. So, congratulations to Tamanna and
Thank you, sir.
obviously her supervisor, Professor Begum, and Professor Sen, for your kind information. I have already gone through all the three reports, including yours, and all three experts recommended awarding a degree.
Yeah,
And
I believe so.
congratulations once again. And I request Dr. Begum to contact with Professor Sen with the report. Please send the copy of the report copy by email, and after getting the scanned signed report from Professor Sen, you please sign it. Tamanna, you please, Tamanna, Najrin.
Turn mute yourself. So then only
after putting your own signature, you please place the both signed report to me for further processing. And I must thank all the participants for for 2 consecutive sessions from 10 started at 10 a.m. Little break for 15 minutes or 20 minutes, and then we rejoined. And once again, it's my pleasure and to thank Professor Sen once again for giving us
Thank you,
your
Professor
valuable
Bombrachari,
time.
for your kind invitation to join this.
Thank you, and hopefully Tamanna will.
Congratulations and thank you, Tamanna, please.
Thank you, sir.
And I'm sure Tamanna has already been enlightened much. And actually, we carried out so many experiments, but we had to also to know something about the basics. And that's the views Professor Senars actually communicating. And we all the teachers actually always try to make understand our students that you also please know something basics of the instrument you are handling. And that's the message we are giving you. Excellent, Tamanna. Congratulations once again, and thank you all for being with us during the 2 sessions. And thank you, Professor Sen, for your kind cooperation. See you again.
You're welcome, Professor.
Physically, I suppose so. Thank you.
Thank you.
Pratik, thank you.
Thank you, Rajanti. Okay.
So we are leaving.
So, shall I leave?
Yes, we are.
Okay.
We are
থ্যাংক ইউ
all
প্রতীক, ভালো আছিস তো ভাই?
ভালো আছি মতিনদা।
বেশ, ভালো থাক, পরে দেখা হবে আবার।
দেখা হবে।
Okay.